introduce the speaker to you, Prof. Paulo de los Rios from the Institute of Physics at EPFL. And he's going to talk on a particularly interesting topic from my point of view. I'm also working on proteins. These are very, very interesting systems, molecular machines of life. And the topic of today's talk, as you can see, is also very interesting. The complex life of proteins, folding, trafficking, misfolding, aggregation, and repair. So understanding the physics of proteins is of great interest and also a very interesting topic for this Biophysics Colloquium series. So for those of you who are new to this series, we have started with this Colloquium series last year, and our aim is to have a talk on some topic in biophysics from scientists within Africa and also those from outside of Africa who are supporting the efforts of what we are trying to achieve. And our biggest goal with this Colloquium series is to, it's part of our effort to develop biophysics on the continent. So yeah, it's a privilege for us to have Paulo here today. And yeah, I'm not going to take more time. So Paulo, the floor is yours.
Thank you so much, Tiart. It's the pleasure is mine, of course. I'm excited to be here talking a little bit about what we have done in the past few years and what I tried to come up with in this presentation is a little bit of a long story that dates back now almost about 15 years when it started, and little by little we are putting together the pieces and getting to understand some aspects of this complex life of proteins that indeed involves all of the issues that are mentioned in the subtitle. So let me first just remind to everybody in a really very simple way what proteins are. First of all, when we think about most functions in the cell, they are performed by proteins. Proteins are oftentimes called the workhorses of the cell. Indeed, if you think about enzymes that drive your metabolism, hormones that allow intercellular communications, antibodies of your immune system, and so on, essentially they are all proteins. Proteins are the way the cell translates the genetic code into machines or actors that can play functions and make the cell work. What is important to remember is that proteins work in most cases, when they attain a certain specific shape. The shape of the proteins oftentimes it is said that shapes determines function. Of course, that's maybe it's only a partial view, but for sure it is important to know the shape of a protein to understand or to characterize its function. And how can they attain this specific shape? And that's where the first a big piece of biophysics that has been really a staple in biophysics for the past 50 years comes in, which is the problem of protein folding. Essentially, the central dogma of molecular biology tells us that proteins are coded into genes on DNA. These genes are transcribed into mRNA, and then this mRNA is read by these very complex machines called ribosomes that by moving along the mRNA, they translate the code that is written in terms of a genetic code into the amino acid sequence of a protein that is assembled one amino acid at a time, and it will come out of the ribosome. It will come out of the ribosome as a polypeptide, as a polymer. And as it comes out, or after it has come out of the ribosome, it has to find a specific shape. And this shape is the functional form. Now, we know from the late 50s, early 60s, that proteins are good at finding this, more or less good at finding this precise three-dimensional conformation by themselves. These were the seminal work by Anfinsen that earned him the Nobel Prize in Chemistry in 1973. Essentially, but you can unfold a protein, for example, by chemical means that is induce the loss of this three-dimensional structure for proteins that have been purified, so they are alone in a solution, and bringing the conditions back to favorable for the folding, the proteins will most likely, more likely than not, find back their own three-dimensional structure and functional structure. So if we think in terms of physics, the fact that they do it spontaneously in the absence of any other actor means that they are trying to minimize their energy, or to be correct, since we are at room temperature for nanoscopic machines, they're free energy, but I will interchangeably call it energy during this talk. And that the native state, which is the functional state, the final functional state of the protein, should be at the bottom of the energy. So we can envision the energy landscape of proteins a little bit like a funnel and the protein during the folding process will roll down this funnel until it finds the bottom. Now, one might naively think that the deeper this state is, this energy is, the better, because this will create very stable proteins that will be extremely reliable and stay and long-lived in that state. But actually, this is not the case. In reality, proteins are only marginally stable, which means that this native state is never extremely deep for a number of reasons, because proteins have to be actually manipulated during their lifetime. And one example where this is important is protein translocations, for example, in mitochondria or in the endoplasmic reticulum, in chloroplast, into organelles, essentially. I recall you that mitochondria are the energy factories of the cell. That's where most of our ATP is produced. And if you just look at the membrane that separates mitochondria from the rest of the cell, it's pretty complex environment made by two membranes. But what is important is that mitochondria actually produce only a very, very, very tiny fraction of the proteins that they need to function. Most other proteins are produced in the cytosol because they are encoded in the host, in the nuclear DNA. So it means that these proteins, once produced from the ribosome, will have to go through very narrow pores. And these pores are very narrow because the mitochondria have a very different ionic concentration than the cytosol. So you don't want large pores because otherwise this large difference in concentrations would be depleted and dissipated very rapidly. So these pores are very narrow, which means that these proteins have to be unfolded in order to go through. Now, imagine that a protein that comes out of the ribosome immediately folds very stably, because we say that the native state is very deep in energy. Then it would be very hard for it to be unfolded and go through the pore. Moreover, it would, even from an unfolded state, it doesn't want to spontaneously squeeze into a narrow pore, get into inside the mitochondria, and only then fold. So this is kind of a strange process and being extremely stable, that is not good. Another instance of the problem of stability of proteins comes with protein degradation. Proteins are constantly produced and constantly degraded because depending on the moment and the condition, environmental conditions, your cells might need different sets of proteins. And since the amount of amino acids in the cell is essentially constant, it means that you have to degrade, that is, recycle, if you want, some proteins to produce different ones. And once again, in order to do so, as you can imagine, think about the machines that does it as a scissor that goes amino acid by amino acid along this unfolded polymer. The polymer must be easily unfolded in order to be recycled. If it was too stable in the native state, that would be counterproductive. Now, this is just one aspect of the reason why protein folding is complex and is just marginally stable. But in reality, the landscape of energy that I drew before, that was sort of smooth, is in reality typically pretty rugged. So there are many local minima, maybe with an energy which is higher than the native state. And so they are metastable state, but still there are many of these minima. So while protein folding is spontaneous, as I said before, sometimes it might just get trapped by chance or by environmental stresses in some local minimum. And so that's a problem because, first of all, this is, of course, lost material because these proteins now are not functional, but also because the folding process, you can think of it a little bit as a process by which the atoms inside the amino acids inside the protein try to satisfy their interactions internally. A protein that is wrongly folded might still have some of the amino acids with unsatisfied interactions, and the way for them to satisfy them is to clump into aggregates together with other misfolded proteins. And so you can form these aggregates that are typically toxic for the cell, from bacteria to humans. We can think about Alzheimer's, Parkinson, and many other diseases are associated to protein aggregation. So because of this ruggedness, of course, we have this problem. And here only the title changed. This is a problem that is intrinsic to the physics of proteins as complex polymers. And because it is intrinsic to the physics of proteins, this is not a new problem for cells. This is a problem that cells had to face from the very start. And evolution has devised machines that are called chaperones, that, if you look at the green arrows here, are able to revert proteins from the misfolded state and actually also to the aggregate states and bring them back to the native state. And the talk today will a little bit focus on how one specific chaperones can do this job. But also, just to mention that these chaperones, as I said, are a solution that life has evolved to solve the complexity of protein folding and of the conformational life of proteins. It is important that this problem is very ancient. It is really important to remember that there are essentially 5 classes of chaperones. They are called HSP from heat shock proteins because essentially they are part of the response to heat stress of the cell, and the number is just about their molecular mass in kilodalton. And these chaperones are the same in essentially all organisms on Earth. You can look at any organism, and by and large, with a few exceptions, they contain all of them. This means that most likely they were already present for the last universal common ancestor. So the origin dates back at least 3 billion years ago, if not more. So really this is a solution that life has found for this complex physics problem. Another point that is important to remember is that at least 4 out of these 5 classes are ATPases, so they use energy to work. Now, this is not surprising because, as I say, they, in the end, as I will show you, they manipulate the conformation of proteins. So you can think about stretching and manipulating a polymer, a rope, and you need to perform a rope to change this conformation. If you need work, you will need another energy source that in the cell typically comes in the form of ATP. And in this talk today, I will really focus on HSP70 a little bit. This HSP70 is my possibly favorite protein among all of them. And it's also because I think it's the one where we start having a coherent picture of what is happening and how forces are generated, the energy of ATP is used, and what are the end results because of this. But also what is interesting about HSP70 is that HSP70 is not just in charge of taking care of protein folding and misfolding and counteracting protein aggregation, but actually the problem of translocation of proteins in mitochondria, as mentioned also in the endoplasmic reticulum, is taken charge of by HSP70, as I will show you. And furthermore, it will also help the disassembly of functional oligomers like Clathrin cages, specific trimers, and so on. Or they are very popular now, cellular condensates, whatever their function, has been shown that their presence is also regulated by HSP70. So the number of housekeeping roles of HSP70 beyond the ones that are important for stress like protein aggregation is growing. And as a physicist, when I see that a protein can be involved in so many different functions, the first thinking for me is whether there is a unique mechanism, so there is a sort of a unifying principle behind all of these functions. And the story starts from the problem of translocation of proteins into mitochondria. And the reason is because, okay, this is, you've seen already this image. And essentially what happens is that you have this double membrane of mitochondria, you have these narrow pores, the proteins on the cytosolic side has to squeeze through these proteins, through these pores. There is a part that is called pre-sequence and already is normally unfolded, and it directs proteins to this pore in a very precise way. This is something that Günter Blobel studied in the 80s and won a Nobel Prize, I don't remember when, I think it was the late 90s because of this. But this sort of duck-like particle is HSP17. And HSP17 actually bound to the pore, waiting for a substrate and to engage it in order to help the translocation of these proteins across the pore. Now, this problem was very popular, and there was a heated debate about how HSP70 was working to translocate proteins across the mitochondrial membrane. And really, this kind of research went on from the late 80s, then the 90s, and early 2000s without real solution. As I say, the part that everybody agreed upon was the first part, that is the engagement of the initial translocating protein by HSP70. But then there were two different views of the function of HSP70. In one view, HSP70, that as I told you at the beginning is an ATPase, would hydrolyze ATP, undergo a conformational transition upon ATP hydrolysis, and use this fulcrum, this point of contact, to perform a lever arc movement by which it would pull proteins inside mitochondria. And then a second HSP70 would bind and pull and so on. So a sort of pulling hand-over-hand movement would little by little unfold the protein outside and pull it once unfolded inside. There was some evidence for a pulling force, indeed, but actually nobody has ever been able to isolate this trimer, so HSP70 bound to the pore and to the translocating substrate. So there was a sort of difficulty in justifying the power stroke in this way, but also there was, as I will show you, structural evidence that HSP70 is very bad at transducing forces in this way. So it went out of fashion. The Brownian ratchet, instead, is a sort of a simpler mechanism. HSP70, again, would bind, detach from the pore, leave space for a different HSP70 that would bind. Now, everything that is required is that the unfolded protein, that of course has to unfold by itself, not because of the pulling, would fluctuate back and forth across the pore. Any forward fluctuation is trapped by HSP70 that forbids retrotranslocations, and in this way, little by little, the protein is imported. The problem is that HSP70 is involved in many other functions, not just in the functions that have been I mentioned, translocation. And in many other cases, there is no back and forth fluctuations of proteins. Sometimes there is just one single binding site, so it would not even be able to perform this kind of processive mechanism. So the Brownian ratchet, while elegant and simple, is not really appropriate. And that's where, back in 2006, together with Pierre Golubinov, who is an expert of chaperones that was here and at the PFL, there is also the University of Lausanne, that is, and his office was 100 meters away from mine. So we met at a cafeteria and we started discussing. And essentially, we came out with this other model. This is called entropic pooling, where the only thing that I really did there was to take into account also the flexibility of the protein that is translocating once it is on this side of the membrane. And the idea is that once the protein is on this side of the membrane, HSP70 binds, and if you want, you can visualize it here. You have many conformations that are allowed for the protein in this half space. Some of them are forbidden because they clash with the membrane. But the binding of HSP70, that here is not in scale. If it was in scale, it would be larger than the pore itself. Now, this HSP70 will further forbid conformations, and in turn will be sort of restrained and trapped around this conformation. So the final result is that in order to increase their entropy, we know that thermodynamics tells us that all systems want to increase their entropy. In order to increase the entropy of the system, the solution is to pull inside more and more ropes so that there will be more conformational freedom. Now, so there is a pooling and it is entropic in origin. Of course, we could solve it analytically using the usual spherical chaperone approximation, a very simple model of polymers. We could perform analytical calculations, and essentially what we find is that indeed there is a pooling force. Essentially, there is a free energy penalty that is purely entropic in origin by binding HSP70 at a certain rope length from the pore. So N is the length of the polymer between the pore and the chaperone. And as you can see, when we bind very close here, we have a great loss of entropy as an increase in free energy. When we bind farther away, the loss is lesser. And it turns out that there is a sort of a non-monotonic, sorry, a monotonic, but decrease of the free energy. If we take the gradient of a free energy is a force, in this case is a thermodynamic force, gives us the pulling force. And this pulling force, we estimated it to be between about 15 piconewton, given reasonable numbers for HSP70. And actually, we performed also molecular dynamic simulations that confirmed, by and large, our result. So this mechanism has the nice property that it doesn't require any of these strange conformational transitions, fulcrum interactions with the pore and so on. It's just, if you want, a wrecking ball is just there for decreasing the entropy and so forcing the system to increase its entropy by importing more and more protein. What is interesting is that over the years, this mechanism has been observed to be compatible with all the other functions of HSP70. For example, disaggregation of a protein substrate, in this case, of an aggregate, in this case, HSP70 binds and it bumps against the aggregate, helping protein translation by bumping against the ribosome, disassembling protein cages, and so on. So in its simplicity, this model tells that HSP70 can produce a force of entropic origin, and it is compatible with all present observations, while the other two models were not. Now, all of this is very nice, but there is an intrinsic problem with this approach. And the problem is that now I'm saying that if I go back here, HSP70 binds here so that it will be able to pull. But because there is a large increase in entropy, that then it decreases by importing the protein. But if there is an increase in entropy, this is a process that shouldn't occur spontaneously because thermodynamics doesn't, sorry, there is a decrease in entropy. So thermodynamics doesn't spontaneously decrease entropy. The process shouldn't. Unless there is a very high affinity. Of course, if HSP70 had a very high affinity for the substrate, then the decrease in entropy would be compensated by the gain or decrease in the energy of binding. So if HSP70 had a very strong affinity for substrates, then this would maybe overcompensate the conformational entropy reduction due to the binding, and that generates entropic pooling. The problem is that HSP70 works on thousands of different proteins, which means that it is a generalist machine. And typically generalist machines or general binders are not good at affinity. Typically, think about antibodies. Antibodies have a very high affinity because they have high specificity. High affinity and low specificity don't typically go together. And that's where we found that in reality, HSP70 can invest the energy of ATP in order to increase its affinity to proteins. How? And so here we have to zoom and change scale. I said, by and large, what I described for entropic pooling can be explained with a perfect sphere instead of the chaperone. So I don't need to know anything specific about the structure of chaperones. In order to understand what happens here, instead, I really need And I remember HSP70 is an ATPase, which means that it can be bound to ATP. And when it is bound to ATP, it is in a sort of an open hand conformation. The substrate binding domain is composed of two halves, the green beta basket and the blue alpha helical lead. The substrate can bind and unbind. And since it is open and easily accessible, binding and unbinding are fast. Sorry. When it is bound to ADP, so typically after hydrolysis, these two halves close onto the substrate. So it means that if the substrate is already trapped there, since it is a sort of a closed box, unbinding will be extremely slow. Similarly, if it had to go in, it has to go in a closed box, the binding will be very, very slow. So essentially what creates a big difference between these two conformations is the kinetics more than the affinity. The affinities ultimately have been measured. They are similar, but the kinetics can be orders of magnitude different. Now, what is important to understand is that HSP70 has an inbuilt sensor. It realizes that there is a substrate that is bound in the ATP state, and this sensor will give a signal telling HSP70 to hydrolyze ATP. So it switches back, it switches into these ADP conformations. Think of it a little bit as a mousetrap. Now, I would like to remember to you that affinity is measured through the dissociation constant. The dissociation constant is a measure precisely of the affinity. The lower the dissociation constant, the higher the affinity. And it is measured taking the amount of free substrate, amount of free HSP70s, their product on the numerator, and you divide by the concentration of the complex substrate HSP70. And it turns out that in thermodynamics, this is K off, so the unbinding rate divided by the binding rate. Now, think of it in such a system. In such a system, the substrate will bind to the ATP-bound conformation, where binding is fast. So K on is the largest possible that you have in this system. But then it can only unbind from this conformation, which is closed. So K off comes from the ADP-bound conformation. So you see now that if you take the largest numerator and the smallest denominator, you can build a very low dissociation constant, which means a very high affinity by switching conformation thanks to ATP hydrolysis. And it can be mathematically proven that this mixture of timescales, where you compose a function by taking one timescale from one state and one timescale from the other, is possible only by if you go away from equilibrium because you consume energy. So you are not just governed by thermal fluctuations, but also by some external energy source. Sorry. And we call this ultra affinity to say that indeed this is an enhancement of the affinity by a non-equilibrium process. Actually, we could solve the full chemical network of the system. We had, luckily enough, tabulated in the literature all the rates for binding and unbinding and so on of HSP70 and substrate. And what we could find is that indeed, okay, I forgot to put here on the x-axis what was represented. Essentially, here on the x-axis is the acceleration of hydrolysis due to the presence of the substrate with respect to when the substrate is absent. So I say that it hydrolyzes only when the hydrolysis is present, when the substrate is present. Actually, it hydrolyzes just much faster. And this is a sort of a measure of the sensitivity of HSP70 to the binding of the substrate. And as you can see, when it is really, really sensitive, we go to this mathematical limit that I've told you before. Otherwise, still, we are in this physiological region where we go down in affinity by at least 1 to 2 orders of magnitude with respect to what would be possible without energy consumption. So when we think now about this machine as something that applies a force and pulls something, and so it is performing work, and because it is performing work, it would need to consume some energy. Now we are seeing how it does it. Essentially, the process is built in two different steps. Energy is consumed to bind, to have a high affinity, effective affinity, which is a non-equilibrium affinity, to bind where it is not convenient to bind from an entropic perspective. And then, after this energy-consuming step that is used to bind, relaxation of the system toward higher entropy states will produce the force. And so this is a sort of a two-step motor. One step is consuming energy to bind, and one step is relaxing to pull. By the way, as I mentioned here, this is the structure with ADP. And now you see why the power stroke would not work, because now this is a very flexible linker between the two domains. And so this, if you think of it a little bit as a lever arm that would perform some transformation, it's pretty clear that it cannot work because it's too floppy to transduce any sizable force. So actually, the view of the lever arm is disproven, so the power stroke is disproven also by structural considerations on HSP70. So now we have this view of HSP70 that is able to use the energy of ATP to perform some work by applying the entropic pulling force. What does it do actually to a substrate? We saw in translocation, but if we think of it in terms of, for example, disaggregation or protein or rescue or repair of protein misfolded proteins so that they can fold again, actually what turns out that there is a host of different experimental proof and also computational evidence showing that the progressive binding of HSP70 to one polypeptide, so one polymer, leads to its unfolding. And the reason is pretty simple. Here, take this picture here. HSP70 is the dark blue, and the substrate here, which is misfolded and pretty compact, is the lighter blue polymer. If you just bind one HSP70, there will be not much conformational transformation. But if you start binding many different HSP70s to this polymer, and typically a typical protein has a good binding site for HSP70 every 30 to 40 amino acids, you start finding that, and this comes from molecular dynamics simulations, it opens up. And you can understand why. If it was still crumpled, all these big HSP70, the red ones here, would bump onto each other. So it is a low entropy state that these chaperones don't want. And in order to increase their entropy, so it's still entropic pooling, they will move apart from each other. And in doing so, they will stretch the coat polymer in between. So there are, as I say, these are other details that I will skip for the sake of time. Well, maybe there is one thing that is worth mentioning. Here we have one single HSP70 bound to a substrate. The substrate is crumpled because this is good for its energy. As it unfolds, from the point of view, while this is the equilibrium state of the system, from the point of view of the substrate, this reduces, this is bad, it increases its energy. So here we have that as the polymer radius increases, the energy increases, and the binding of farther and farther HSP70s leads, on one hand, sure, to the increase of the radius of the system, so the stretching of the polymer, but at the same time, it increases the energy of the polymer. So if we want to model this process, we have to take this into account. And what did we do? So we set up a system where we took one of these polymers or proteins that were used in the experiments, this called rhodanese. Computational, we found that there are 6 binding sites, and every binding site can be empty, occupied by an HSP70 with ATP or an HSP70 with ADP. So in the end, there are 3 to the 6, 729 states. We model explicitly the concentrations of ATP and ADP. And so we follow a reaction network of different conformations where each binding site, the black ones, can be empty, bound by molecule by HSP70 and ATP, ADP, transformations from ADP to ATP by hydrolysis or nucleotide exchange, and so on. So we have all this data from the literature. The binding that was tabulated only for peptides, and so for stretches of proteins that are easily accessible, had to be corrected precisely by this free energy that we could compute by molecular dynamic simulations that penalizes, that has to compensate so that everything agrees, because it's indeed binding goes uphill, that penalizes the binding. So we could set up a complex reaction scheme of binding and unbinding of HSP70 that allowed us to indeed perform these calculations. And to cut a long story short, we could titrate the amount of ATP over ADP. And I would just like to remind you that the energy that we obtain from ATP hydrolysis is actually the excess chemical potentials of the solution that we have in terms of concentrations of ATP and ADP, and technical also phosphate, but at least in these experiments, phosphate is buffered. And the concentrations that ATP and ADP would have if we would let this solution to relax at 2 ADP. I recall you that ATP is an excited molecule, so it is a high energy, and spontaneously it decays, although very slowly, in days or weeks, into ADP, in the proportion that at equilibrium you will have 1 molecule of ATP for about 1 million molecules of ADP. So this is would be this ratio at equilibrium. In the cell, for example, this ratio is about 10. So this ratio of ratios would be about 10 to the 7. If you take the logarithm, you multiply by kBt, this is the amount of energy that you can get out of ATP hydrolysis. And it is something that can be controlled, of course, in our calculations, but in principle also in experiments, at least in vitro. And so what we did was to measure the expansion of the polymer depending on whether we are at equilibrium. So this ratio, ATP over ADP, is the equilibrium one. And as you see, the expansion, the radius of gyration of the polymer is essentially the one of the native protein. These are averages of several realization of the process. But if we increase ATP over ADP and we bring it to cellular conditions, so 10 times more than it would be, sorry, 10 times, so a value of 10, so 10 to the 7 times more than it would be at equilibrium, you see that there is a large expansion. So first of all, our model would confirm that there is an expansion. But where did this expansion come from? And that's where is possibly also more interesting, because it now starts connecting with what I told you before in terms of ultra affinity. So the affinity increasing by energy consumption. If we keep the ratio of ATP over ADP very low, so we go toward equilibrium, that would be here 10 to the minus 6. This is the average number of bound chaperones. And as you see, is essentially 0. So chaperones are not able to bind, because by binding, they would increase the energy of the substrate, and their intrinsic affinity, the one that is not stimulated by energy consumption, is not enough to bind reliably. Now, the picture doesn't change if we increase the amount of ATP over ADP, but we create a theoretical mutant that is not able to hydrolyze ATP. Since it is not able to hydrolyze ATP, it cannot use the energy of ATP, and it keeps not binding. So essentially, we find that there is no way that chaperones bind. And if chaperones do not bind, the polymer remains compact. But as we turn on ATP hydrolysis and we go to cellular concentrations, so about 10, suddenly we see that we are binding about 5.5 on average chaperones. So essentially the substrate will be very well populated by chaperones. Chaperones will bind very effectively. And if you remember the pictures, when it is very well populated, it is very well expanded. So it is unfolded. So HSP70, by this trick, uses energy of ATP to enhance its affinity to bind. By binding, it applies forces by entropic pooling that result into the unfolding of the protein. Now, I slowly wind down to the end. So essentially, we now can think of what happens when proteins misfold and aggregate. And of course, this works both for misfolding and aggregation. Essentially, once a protein is, let's say, is misfolded, chaperones will come in, will start binding, and will unfold it again. Then they will release it, and from that state, now the protein has a chance to fold back, to fold to the native state where chaperones leave it without perturbing it. If by chance it again misfolds and possibly aggregates, chaperones will repeat the process and again, a little bit like a Sisyphus, of course, hopefully often, or at least sometimes, a chance of success that unfortunately Sisyphus didn't have. So this is what happens. And if you think of this as a pump, what turns out is that you can populate the native state way more than it would be populated just by thermodynamic equilibrium. You can think that maybe because of a perturbation, heat shock, for example, the native state, or even aggregates, and as you see, I drew actually, Balchin et al. Drew lower in energy than the native state, can be emptied because there is a one-directional pump that, consuming energy, will take proteins that are non-native and give them a chance to become native. And so there is an increased stabilization of proteins thanks to energy consumption and the action of HSP70. But actually, we proved this also experimentally and with a simple model also for at least another chaperone. So it might be a general mechanism of different chaperones. So as I say, it is a pump. Now, let me just skip this part. Let me come to the conclusions. So the life of proteins is very complex. First of all, because protein folding is not as simple as typically it is depicted, but also because proteins by necessity must be pretty plastic. They have to be unfolded easily, which will make it so that all these local minima that you have in the landscape might not be so far away from the absolute minimum that is the native state. I hope that everything is okay. I don't hear anybody.
Yes, I can still hear you, Paulo.
Okay, perfect. Sorry.
Continue.
So chaperones are the invention of nature to solve these problems and to help all these manipulations of the protein structures. They are, from the physics point of view, very nice machines because, as you saw, ultimately, we really needed a series of different approaches from polymer physics to molecular dynamic simulations, stochastic modeling of proteins, rate equations approaches. So many different approaches to bring together all the different scales at which interesting phenomena happen. So I think also for physicists, both theorists and possibly experimentalists, chaperones, I think, represent a very, very interesting arena. And with this, let me come to the acknowledgements. First of all the people who contributed to this work. As I said, Pierre originally 17 years ago, and all the people that came on board over the years. Now, just let me advertise a recent work that we posted on bioRxiv. I really have to thank Chan Cao and Verena Ruckers from the University of Geneva and EPFL. Verena is a very talented PhD student of Chan. They work on nanopores, and so they could prove using single molecule techniques that entropic pooling is real, is not just a theoretical construction, which of course was till this moment. So in case you are interested to look at, to advertise this work. And of course, I would like to thank you all for the attention. Thank you very much.
Right. Thank you very much, Paulo. Yeah, very interesting. Yeah, very rich underlying physics. And I'm actually glad that you did not show all the relevant equations, because not everyone here is well equipped with the physics, but thank you very much. Very interesting. If you would like to ask a question, please raise your hand or simply write your question in the chat. Right, I see that Eddie has a question. Please go ahead.
Thank you for the opportunity to ask this to ask a question, and I really appreciate the presentation. I'm just wondering, in the model presented, and by the way, a great talk. What is happening on the cytosolic side in this case? Because I think I appreciate what you presented on the mitochondrial side. Is the substrate presented as an unfolded in an unfolded conformation? Is HSP70 on the cytosolic side playing a role in this? Thank you. I have background noise, so I'll limit my question to this for now. Thank you.
Yeah, no, it's the point is very well taken, because this is really one of the main issues. I hope that you can see my cursor here. Can you see my screen and the cursor?
Yes, I can see that. Yes.
Okay, perfect. So what happens is that on this side, the proteins can be in many different, they could be unfolded, they could be partially folded. Sometimes they are bound by cytosolic chaperones that keep them unfolded. But of course, then, you have to get rid of the cytosolic chaperones. Sometimes are anchored but to receptors, if you want, protein receptors that surround the pore on the cytosolic side. Now, why is it, for example, you could ask, why is it that there is no symmetry? So why is it that chaperones are not pulling on in this direction? That would be possibly one question. And the reason is that, of course, there is a player that I didn't mention, because otherwise the molecular biology and biochemistry of the problem would increase. Actually, the hydrolysis by HSP70 is accelerated by the substrate when it is in conjunction with what is called a J-domain protein. So J-domain protein is that this J-domain that specifically targets HSP70, and in conjunction with the substrate accelerates ATP hydrolysis, so to allow ultra-affinity and the process that ensues. Now, it turns out that both in the case of the mitochondrial protein import and in the case of ER import, these pores also have a J-domain, but on the mitochondrial side, but not on the cytosolic side, which means that HSP70s that are present in the mitochondria will be able to bind in these restricted conformations, because they will be able to use ATP hydrolysis to reach ultra-affinity and trigger all the downstream processes. While this is not possible, this is not going to happen on the cytosolic side. So that's why the process is directional, precisely because of this asymmetry that is inbuilt in the molecular protein composition which is different on the two sides. I hope that this addressed your question.
Right, thank you, Paulo. Lawrence has his hand up. I see you have also typed some text in the chat, but please unmute yourself and ask the question out loud.
Okay.
Hi, so I did put my question in the chat, and I just wanted to know, so how do the chaperones do their work? Are you able to follow that in your molecular dynamics simulations and see like what terms sort of pop from the force field? From the simulations, can you see like, is there like a critical phenomena where water somehow gets excluded and then a whole bunch of other things start?
The molecular dynamics simulations that we performed are coarse-grained molecular dynamics simulations.
Okay.
So essentially, water is implicit, and we don't take into account only excluded volume between proteins, between the different protein components and the membrane, nothing else. And with that, of course, which is almost true by construction, we confirm the results that we obtained with the simple spherical approximation, because in a way that's everything there is. Now, we are going to revisit this a little bit, because the spherical approximation and also the coarse-grained molecular dynamics simulations told us that HSP70 was able to apply a force of about 15 piconewton. Mm-hmm. Now, the experiment that I was mentioning in the acknowledgement page by single molecule give a much stronger force, which kind of surprised us. And now we are trying to see whether this is a problem of extra terms, like, for example, electrostatic repulsion of HSP70, which is mostly negatively charged, and the membrane and the pore that turn out also to be mostly negatively charged. And so relying just on the size, if you want, on the van der Waals size of the protein, really almost the atomic size, might be an underestimate of the real volume and so of the real spherical clash that is induced by HSP70 once electrostatics, that even if screened, might add maybe 1 nanometer, one extra nanometer in terms of excluded volume, in terms of radius, and this might deserve a more detailed molecular dynamics simulations. I think instead going into explicit water might bring something. Of course, I cannot say no. I think that given the length of these simulations, in order to be statistically reliable, taking water into account, I think is beyond what we can do right now.
Excellent. Lawrence, does that answer all your questions?
Yes.
Okay, great. Okay, Eddie has posted another question in the chat. Is it possible that the J domain protein in mitochondria could serve as an anchor?
Yes and no. Yes, because it works in both cases, mitochondria and the ER. Yes, in the sense that most likely they act for sure in the ER and possibly also in mitochondria, although in mitochondria there might be extra contact points, as a way to localize HSP70 at the exit of the pore or entrance, depends on the point of view. But after hydrolysis, HSP70 detaches from the J domain. So the J domain has very, very low affinity for HSP70 in the ADP state. So essentially, once again, you would not find the trimeric state. It would disassemble immediately.
Right. Are there any other questions? So there's a general question in the chat, not related to the topic of today's talk, but more in general on biophysics. So maybe we can take that question in the meantime. So that's from Umar Dras, and
well, yes. It was, I'm not very familiar with biophysics, but I want to point out. So I need guidance there. What should I do? I have completed my in physics. I'm aside. There is not much research opportunities in biophysics, so there is no guidance in this regard. I understand the problem because, of course, biophysics is sort of old and new. Of course, it's not a completely new branch of physics. We're talking about biophysics since at least 30 years, but at the same time, 30, 40 years in earnest, a little bit even before, but let's say with a vengeance, let's say, more recently. But still not on the same scale as particle physics, cosmology, solid state physics, and so on. So there are not many universities that have a very good program or curriculum in biophysics, maybe after the bachelor, like master program. Maybe they have 1 or 2 courses, but not more. So in this respect, I would say, of course, the easiest solution would be, depending on possibilities, to look for institutions where at the master level there are curricula either still in physics but with a strong background, strong orientations, or many courses in biophysics. Sometimes there are nowadays also emerging the really masters in biophysics. So directly going for a master in biophysics. As a general piece of advice, I think that it is extremely important to have a very strong, let me call it traditional physics background as a bachelor level. That's where your competence in physics will be useful to go toward biology, because in the end, unless you fall in love with biology and you want to be a biologist, this is not what we are by training. They do their job much better than we do in terms of biology, but we can complement what they do. At least this is the entrance point. But of course, 20 years down the line, one might become a biologist. But the entrance point, maybe at the master or PhD level, typically will be by working together with biologists. And what we can bring is the physics angle that can be ability to work with equations if you're a theorist, with some kind of experimental techniques that maybe a biologist is not comfortable with. Sometimes it's a different way, not better, but different to look at the same problems. But this comes because of the training in a strong training in basic physics that comes with a bachelor, a good bachelor, 3-4 years in physics, depending on the places. In Europe, we are 3 years of bachelor. In other countries, maybe it can be 4. Then I would say that in most cases, to do biophysics, you don't need very, very complex physics, like string theory, or very complex math, like string theory and so on. It's more like, and that's why it is important to know well your basic physics. It's more like reverse engineering. So you really need to be able to bring together many different branches of physics that you can study during your bachelor, plus a few things that you have to study by yourself, but not many, but really be able to bring them together. And so at that point, during the master, it might be a good moment to go toward some more robust biophysics. Keeping still the mind open, maybe there is this extra course in physics that raises your curiosity, and you never know. Think about general relativity. A lot of the formalism of general relativity is useful to deal with membranes. Membrane physics, since they are curved surfaces, is curved spaces, borrow many or have in common many of the mathematical techniques that, of course, in a much more complex setting, you learn doing general relativity. It's not necessarily the only way to do it, but there might be unknown and unexpected bridges. So keep your mind open, but maybe at the master level is the good moment to go toward biophysics. If your institutions don't have a robust program in biophysics, and you want to do it, I would say the only piece of advice is look for nearby institutions where there is something, because anyway, it's not that you will find it anywhere. And of course, because it is a transition, I'm sorry if it takes long in answering this question, but if it's a transition, you would need a little bit of guidance. It's very difficult to be a self-taught biophysicist, especially when you come out of a bachelor. Of course, it's possible, but might not be optimal.
Thank you, Paolo, for elaborate reply on that question. Okay, so let's take 2 more questions or 2 other questions in the chat, and then we can finish with that. Okay, so how did you achieve the FES for a single molecule of HSP70, the free energy surface?
Okay, so let's see if I get the question right. So the only energy, so of course, when we do, for example, molecular dynamic simulations, just as I was answering before, we integrate Newton's equations, more technical Langevin equations, and the only ingredient that we have are the structure of HSP70 and we forbid them to cross membranes and so on. Actually, if we think about this free energy surface for entropic pooling, this is the way we compute it. Since it's an entropic effect, take this picture here. We can compute the number of conformations of the polymer that are allowed in the absence of HSP70. And by the way, we know where, let's say, HSP70 could bind. We define a few binding sites. Then we repeat the same calculation, for example, by molecular dynamic simulations, with the chaperones that are bound. Or actually, we can perform the simulations in this case, and on a series of uncorrelated snapshots, we bind HSP70 on the binding site. And we check, does it clash with the membrane or not? And we count the number of conformations that are allowed in this case, and the number of conformations that is smaller that are allowed in this case. If we take the ratio of these two numbers for a given length between the rope length between the pore and the chaperone, this is essentially the ratio of the partition function. So if we take the logarithm and we multiply by kBt minus sign, we get this free energy density. And actually what we did at the time, we also performed simulations. We really measured the mechanical force that is applied on the polymer, and it indeed is, of course, much noisier because of noise of the simulation, but is indeed the derivative of this free energy surface. So this is a trick that we use to compute it.
Okay, hope that answer was satisfactory. Let's take the last question again from Eddie. What is the level of ATP in mitochondria versus cytosol, and would this influence the dynamics?
That's a good question. I don't know. We assume that it's the same, but might very much not be the same given the fact that there is ATP production in mitochondria. It might be different. So I admit my ignorance there. I don't expect it to be radically different, but it might be for sure different.
Right, yeah, the reason why there are still scientists on this planet is because we haven't answered all the questions that are existing. So yeah, let us encourage more research in this area, and let's thank the speaker again for a great presentation that has stirred a lot of questions. Thank you very much, Paulo.
Thank you so much to everybody. I hope to see you soon somewhere. Goodbye.
Excellent. Thank you. Goodbye.
Bye.
So our next talk is next month on May 29th.
That's right. And we are still looking for a speaker for that date.
Right. So
if there's anyone in the audience who's interested in giving a talk, please drop us an email. Or just express your interest here
in the chat, or it was in the invitation. Fine. Make sure I put the right email in there. Right. In the chat, you use that email. The organizers will get it. Or if you know Chart, you know Professor Trevor Sewell, you can contact them directly. Also, I guess I'll put in the chat from our friends in the United States at the National Institutes of Health. There is a HIV structural biology meeting coming up. I put the advertisement in the chat. I don't know. I think it's in person, but I think they live stream it as well. So at least they did last year. Okay.
Great. Thanks a lot, Lawrence.
Okay.
And if you have more ideas for speakers, please let me know. I can also reach out to them. I still have to reach out to that snake venom person. But as soon as possible.
The snake
I
venom
can talk
person.
to the snake venom person. I'm talking to him quite a lot.
Yeah, that whole topic freaks me out. Snakes freak me out.
Don't worry, don't be silly, Lawrence. Snake venom is interesting. That's why you need antibodies against them.
The snake anti-venom is interesting. Snake venom, not so much. All right, thanks. We'll talk to you guys later.
Right, thanks, Lawrence. Thank you, everyone. Goodbye.